What's up, everybody? This is Mr. Richardson coming at you live through the power of the internet. And what we're going to be doing today is talking about drawing conclusions about sample surveys using a computer simulation. If you're just getting here now, make sure you go back and watch my previous video on sample surveys. We're going to be talking about them a lot in this video, and it's important that you understand how they work. I'll leave a link to that video in the description below the video, but let's jump right into it today with a problem. In order to introduce computer simulations, we're going to start with a proposition. Imagine that you have a friend, Sneaky Pete, and Sneaky Pete wants to make a bet with you. The way the bet works is Sneaky Pete is going to take a penny and flip it 10 times. If it lands on mostly heads, Sneaky Pete is going to give us $10. However, if it lands on mostly tails, we have to pay Sneaky Pete $10. If it's a tie, nothing happens. Would you take this wager with Sneaky Pete? Well, let's see what happens. Sneaky Pete flips the penny 10 times, and the results are as follows. It comes up with 2 heads and 8 tails. What that means is we now have to pay Sneaky Pete $10. My question for you is, does this seem fair? Based on the experiment, is it possible the coin is fair? Or do we believe that Sneaky Pete pulled one over on us? Why or why not? Explain your answer. In order to answer this question, we have to think about what would happen in the most predictable way possible. Well, if I think about how many tails should come up at random on this experiment, it should happen half the time. So if I flip a coin 10 times, in the most predictable way possible, I should get 5 tails because that's half of the 10 trials. But does that mean that I should get 5 tails every time? The answer is no. Certainly we could flip a coin 10 times and I would only get tails 4 times or 3 times. I could also flip a coin 10 times and maybe I do get 8, but we know the most predictable way is I should get it half the times or 5 of those 10 trials. So the question we have to ask ourselves, is 8 unreasonably high? When I see 8 out of 10 trials, that proportion is 80% of the time, and it's not happening 50% of the time. So we really need some type of way to check if 80% is too high. Otherwise, we can't make a determination whether or not this coin is fair or whether or not Sneaky Pete fooled one over on us. And that is the whole point of computer simulations. So what is a computer simulation or a sampling distribution? Say we want to take every possible sample of a given size from our population. Every sample would have its own measure, meaning if I did this experiment again and flipped a coin 10 times, I'm likely to get a different measure. And the distribution of all of these different values is the sampling distribution of the statistic. It's what happens from doing multiple samples all the time. Well, why are sampling distributions important and why are they useful? Well, remember, we want to make a distinction about what happened when we flipped this coin 10 times. That's like one experiment. Well, if I know what happens when I did this a lot of times, like if I did this experiment 100 times or 200 times, I can get a better idea of what's going to happen when we only do it once. Of course, we can't always take a sample multiple times. I can't always do an experiment 100 times or 200 times. So we rely on the computer simulation to do this experiment for us 100 times, 1,000 times. And then when we do our experiment once, we can see whether that statistic was valid. Well, how do we use a computer simulation? Start by assuming a value of statistic of interest. Then we do a large number of simulations assuming that value. These simulations are typically done using a computer, and they show us what would typically happen if we did this experiment a lot of times. Then we look at our single sample and compare it to the population sample to see if we can draw some type of conclusion. Let's look at steps to do this. The first thing you need to do when you do a computer simulation is you need to assume a value for a statistic of interest. What should happen? Not what happened in your experiment, but what should happen. In our coin example, it should be 50%, or it should happen 5 out of 10 times. That is the assumed value and not the value from our sample. In step 2, we want to run a computer simulation based on the assumed value. So assuming that tails will show up 50% of the time, I want to run a simulation, maybe 100 times, 200 times, 500 times, 1 million times. The next step is to see how many times the value from our sample showed up in the computer simulation. We want to decide if it showed up a lot of times or a few times. If our sample value is less than the mean, I'll include the simulation values that are smaller than it. If the sample value is greater than the mean, I'll include the simulation values that are greater than it. We'll see more of this in an example. Step 4 is to determine if there's few cases or many cases that support the statistic from our sample. Did this happen a lot of times or a few times? Anything less than 5% of the simulation values would be considered few cases. Anything more than 5% would be considered many cases. Of course, this percentage is going to be based on how many times you did the sampling distribution. Finally, in the last step, find if the claim is reasonable to happen or unlikely. In ours, we're trying to decide, is the coin fair or is it possible that something shady went on? What does the simulation tell you about the likelihood of getting the result in the sample? This is based solely on having few cases or many cases. Nothing here is absolute. There's no this definitely should happen or this definitely should not happen. It's either this is very possible or it's not very possible, and it's not based on a hunch. It's clearly based on the data from the computer simulation. Let's try our first computer simulation. The first thing we have to do is assume some statistic for our simulation. In this case, we're going to assume 50%, which means that a coin should show up on tails 50% of the time. Now we're going to use the computer to simulate what might happen if I flip a coin 10 times. So let's try it. Let's flip a coin 10 times. Here I flipped a coin 10 times and look at what happened. Of course this happened. This is the most predictable thing that could happen. I got 5 tails. So the proportion of tails that I got is 50% or 0.5. This dot here means that I flipped a coin 10 times and I got 5 tails, which has a proportion of 50%. Let's do this again. Let's flip the coin 10 times and see what happens. Look what happened this time. I only got 3 tails. That is a sample proportion of 0.3. So now, if I got 3 tails, I need to label that here that it happened 1 time. I've now done this experiment twice. Let's do it a 3rd time. Here I'll flip a coin 10 times. 3 tails is a proportion of 0.3. Let's add this to our sampling distribution. What you're now seeing is 2 dots here for 0.3 because when we did this experiment, 2 of the 3 total times, twice we got 3 tails. Let's do this again. In this trial, when we did it 10 times, we got 1, 2, 3, 4, 5, 6, 7 tails. That is a sample proportion of 0.7. Let's add that. Let's do this a 5th time. In this trial, the computer is saying that we got 7 tails again, which is a sample proportion of 0.7. Let's try this a 6th time. In this case, we got 4 tails or a sample proportion of 0.4. Let's add 0.4 to our sampling distribution. This 1 dot here means that of the experiments we did, 1 time I got exactly 4 tails. Let's try another. This time I got exactly 6 tails, which is 0.6. What you can also notice is look at what's happening up here. As I continue to do this experiment, everything is changing. Let's try an 8th trial. On this 8th trial, I got the most predictable way. I got exactly 5 tails. That is a sample proportion of 0.5. Let's try a 9th trial. Here, I only got 2 tails. That is a sample proportion of 0.2. Notice how when 0.2 is added, the mean has now gotten smaller than 0.5. Let's do a 10th trial. Here I got 4 tails or a sample proportion of 0.4. Now, of course, I want to do this a lot of times, 100 times, 1,000 times, 1,000,000 times, and I don't want to have to do it by hand every time. So what I can do is just tell the computer, hey, just generate a bunch of them for me. So let's just generate another 10. Rather than do them singularly, this is just going to do 10 trials, and each trial, remember, counts as 10 flips of the coin. So let's populate it. I just added 10 trials. You'll see I now have 20 simulations. Here it looks like now I have, of those 20, 7 of them came up as 5 tails. Let's generate it again. I now just generated another 10 simulations, so I'm now at 30 simulations. And if you look, finally a proportion of having 8 tails or 0.8 has showed up 1 of the 30 times. Let's try it again. I'm now at 40 trials, I'm now at 50 trials or 50 simulations, 60 trials, 70 trials, 80 trials, 90 trials, and finally I'm at 100 trials or 100 simulations. We can see of these 100, 0.5, which represents 5 tails, happened the most, which we expected at 31 times. The next most popular one in our simulation was 6 tails, which happened 22 times. The least popular was either 1 tail, which happened once, or 9 tails, which happened once, and here 8 tails, or a sample proportion of 0.8, happened 4 times. Let's see what we can do with this information to draw a conclusion about Shady Pete and our sample. Looking at the computer simulation, we can see that the value of 0.8 from our sample is right here. Because 0.8 is larger than the mean, which here is 0.511, we are going to include the values to the right of it. The reason we include the values to the right of it is we can see 0.8 only happened 4 times, but even something more extreme like 0.9 or 9 tails happened once. So we want to include the values that are even more extreme than the statistic that happened in our sample. After we've highlighted the cases that happened in our computer simulation, we want to decide, does this represent few cases or many cases? Here I can see this didn't happen very often. It only happened 5 times out of 100 simulations. So what we can conclude is that this simulation shows few cases with a sample proportion of 0.8 or greater. We said greater because this value of 0.8 was to the right of the mean. Had the value been to the left of the mean, we would have said or less. So the claim that 80% of the flips will be tails is pretty unlikely. Think about it. We did this 100 times and 0.8 happened a very small percentage of the time. So we can conclude that this coin is quite possibly not fair. Do I know for sure that the coin is not fair? The answer is no. Of course it could happen that I get 8 tails, but it's pretty unlikely. So I would say that I could conclude that this coin probably isn't fair. Of course I'm not sure, but if I had to take a guess, I'd say Shady Pete. He pulled one over on us. Let's now try an example from start to finish without doing the simulation and having the simulation being done for us. This problem reads as follows. A survey of 80 high school students was given to determine how many people were in favor of forming a new STEP team. The school will form the team if at least 30% of the students at the school want the team to be formed. Out of 80 surveyed, 22 said that they wanted the team to be formed. To test the significance of the survey, a simulation was done assuming 30% of the students wanted the team, each with a sample size of 80, repeated 100 times. What conclusions can be drawn using the simulation results? So in a problem like this, we have to understand a few things. First, the computer simulation is already done for us. That's what's represented right here. We don't have to actually do the simulation. The results are shown here. The second thing we have to understand is what each of these little dots represent. Each one of these dots represents a trial of one computer simulation. The next thing to notice is what actually happened when we did this survey. Well, what happened was we surveyed 80 high school students to determine if they were in the favor of the STEP team, and only 22 said they wanted the team. So when I look at this, 22 out of 80 is about 27.5% of the students. So when they did this survey, what they found was that they did not have enough students to support the STEP team. Think of what could have happened though. They could have had 30% of students that wanted the STEP team or had a lot of them in favor of it, but the 80 students they asked weren't the right group of students and they got a number that was below 30%. Well, next thing we want to do is find where this proportion from our computer simulation is. If I look at where our sample proportion fell, it fell right here. And because that's to the left of the mean of 0.3, I'm going to include all of the values less than it. If I add up all of these little dots here, I see that I have 27 of them. What that means is that 27 times out of 100, or 27% of the time, I got a value of 27.5% or less. 27% is a big number. It's much larger than 5%. So what this means is that the simulation shows many cases with a sample proportion of 0.275 or less. Again, I used less here because it's even possible to get smaller numbers than that 0.275. So the school can conclude that the requirement of having 30% of the students in favor of the STEP team is very reasonable. Think about what happened here. We assumed running this experiment that 30% of the students wanted the STEP team. And in that regards, there was a lot of times that if we only asked 80 students, that we'd still get a number of less than 27.5%. Let's see if you can try one. This example reads, Mervette flipped a coin 80 times and 36 of the 80 flips were tails. She wanted to see how likely a result of 36 tails in 80 flips would be with a fair coin, so Mervette used a computer simulation to see the proportion of tails in 80 flips repeated 100 times. Based on the results of the simulation, what inference can Mervette make regarding the fairness of the coin? So we know, of course, when flipping a coin, we expect to get tails half the time. So in 80 flips, we would expect to get tails 40 of the time. And of course, when Mervette did this, she only got 36 tails. So we're trying to think, is 36 unreasonable? Is it too small of a number to get? Or is it likely to happen? So we run this computer simulation. Well, the computer simulation is run based on 50%. That's the assumed value here. And then we want to see if what we got in the sample could happen. Well, in the sample, this happened 36 out of 80 times, or 45% of the time. That's clearly less than what we'd expect, which we'd expect 50% of the time. Because we expect 50% to be the average, 45 is less than that, so we not only highlight the cases where 45% happened, but we also highlight the cases less than that. Now we need to see how many times this happened. So let's count. If my math is correct, I counted that this happened 26 times. Now, because we did this 100 times in the simulation, that happened 26% of the time. So if I flipped a fair coin 80 times, it's very likely to get 45%. And we are basing this only on the simulation, because think about it. The simulation shows many cases. Remember, there's 26 cases out of 100. That's a lot. So it's showing many cases with a sample proportion of 45% or less. Look, we have 26 cases out of 100. That's a lot. That's 26% of the time this could happen. So our claim that 45% of the flips will be tails is very reasonable. It happens a lot. So we can conclude that this coin is quite possibly a fair coin. Even though we didn't get 50% of tails, we only got 45%, this is something that could happen quite reasonably, so this coin is most likely fair. Let's try another example. This question reads, the senior class president of Gramercy Arts High School claimed that 75% of the senior class was interested in going on the senior trip. To test this claim, the senior class president conducted a survey of a random sample of 100 seniors, and 67 said they wanted to go on the senior trip. To better understand the significance of the survey results, a simulation was devised based on the claim that 75% of the seniors wanted to go on the trip. Each of the sample size 100 simulated 100 times. Explain how the results of the simulation can be used to support or refute the senior class president's claim. First thing I like to do is see what happened in the sample. We saw that we had 67 out of 100 seniors say they wanted to go on the senior trip, which is only 67%. So if it was based on just this 100 students, we wouldn't have 75% of the class interested going on the trip. In our sample, only 67% said they wanted to go on the trip. But is it possible that if we actually really did have 75% of seniors wanted to go on the trip, and we only asked 100 of them, that we could get a number as low as 67? Well, that's what the computer simulation is going to tell us. We ran this simulation based on an average of having 75% of the seniors wanting to go on the trip, and then we want to see, is it possible to get a number as low as 67? So we find 67 on our chart, and 67 is right here, and because it's to the left of the mean, we're going to include the cases to the left. This isn't looking good. Look how many cases we have. This is only 3 cases out of 100 times, which means if we actually had 75% of the seniors wanting to go on the trip, it's not going to be very likely that we asked 100 of them and only 67 said so. Well, why is that? Well, it's because the simulation shows very few cases, really only 3% or 3 out of 100 cases. So it shows few cases with a sample proportion of 0.67 or less. So the claim that 75% of the senior class wants to go on the senior trip is very unlikely. It's not saying that we couldn't still have 75% of the kids wanting to go on the trip, but based on the simulation, it's very unlikely that we do. Let's try another example. Question 3 reads, Brian rolled a die 50 times and 10 of the 50 rolls came up as a 6. He wants to see how likely a result of 10 sixes in 50 rolls would be with a fair die, so Brian used a computer simulation to see the proportion of sixes in 50 rolls repeated 100 times. Based on the results of the simulation, what inference can Brian make regarding the fairness of the die? One thing I like to do is see what happened in our sample. Well, we saw that we got a 6 10 out of 50 times, or 20% of the time. This is pretty high. The assumed value here is that a 6 should show up 1/6 of the time because there's 6 sides on a die, or 0.16 repeating. But that's not what happened in our trial. When we did this 10 out of 50 times, or 20% of the time, the dice showed up as a 6. So we're trying to see, is this too high to be likely that it could happen, or is it within reason? So what we do is we run the computer simulation based on this value here. And what we're seeing is that 20% happened a lot of times, and even things higher than 20% happened as well. So now we want to count how many times this happened. By my calculation, this happened 39 times. So the simulation shows many cases with a sample proportion of 20% or greater. So the claim that 20% of the rolls will be sixes is actually quite reasonable. So we can conclude that the dice is quite possibly fair. Let's try one final example. This question reads as follows. There is an upcoming election for Teacher of the Year. Mr. Richardson must get over 50% of the vote to be nominated. A poll was taken of a random sample of 100 students from the high school, and 44 students said that they would vote for Mr. Richardson for Teacher of the Year. Simulations were done with a population percentage of 50% and a sample size of 100 to see how likely a sample of 100 would have 44 who voted for Mr. Richardson. The results of 200 simulations are shown below. What conclusion can be drawn regarding the likelihood that Mr. Richardson will be named Teacher of the Year with more than 50% of the vote? Well, let's see what happened here. I asked 100 students if they'd vote for me for Teacher of the Year, and only 44 said they would. So that means that 44% of those students thought I should be Teacher of the Year. But I actually need 50% of the votes in order to be Teacher of the Year. So I want to see, is it possible that half or 50% of all students would vote for me? And if I asked a smaller sample of 100 kids, maybe I asked some of the wrong students that hadn't been in my course before, and I only got back 44% would vote for me. So we're going to run this simulation based on having 50% and see if 44% is actually possible. First thing I want to do is find 44%, or 0.44, which is right here. And because it's to the left of the average of 50%, I'm going to include the values to the left. So this right here is all of the values of 44% or less. Let's count how many of those there are. When I counted how many times this happened in the simulation, I got 34 times out of 200 simulations. Well, 34 out of 200 means that this happened 17% of the time. So what conclusion can we draw? Well, the simulation showed many cases with a sample proportion of 0.44 or less. We can see that this happened 34 out of 200 simulations, which is 17% of the time. And anything greater than 5% means it's happening a lot of the time. So what does that mean in regards to me getting Teacher of the Year? Well, this is actually very tricky. Think about how many of the votes I would need to be Teacher of the Year. I would need to get more than 50% of the votes. And what this is saying here, that it's very likely that if 44% of our sample said they'd vote for me, that I might have 50% of the students. But even if I have 50% of the students, I'm not so sure that I'm going to win the election for Teacher of the Year, because somebody else might, which means that these results are most likely inconclusive. I can't tell if I'm going to win or not, because even if I did have 50% of the votes, I'm not going to win the election. Had instead of having 34 cases, had we had very few cases, we could say that I'm definitely not going to win the election. Because if we had very few cases, it wouldn't even be likely that I had 50%, so then it's very likely that I won't win the election. Well, that's it for simulations, and that's it for me. I hope you learned a lot in this video. Computer simulations is one of the coolest statistic topics in my opinion, and I hope you think the same thing after seeing this video. Until next time.